Imagine you're in the kitchen with a friend, preparing a delicious meal together. If your friend is a novice to cooking, it might be necessary to spell out each step of the recipe in painstaking detail, as Remy the rat here had to do with his clueless human partner, Linguini. But a hallmark of human collaboration is the ability to gradually leverage small amounts of experience to chunk together higher level abstractions. In this case, once Linguini understands the procedure of making a roux, he no longer needs step-by-step instructions. Remy can just say the word roux, and the entire process can unfold in Linguini's mind. But how do people actually achieve this feat? Collaboration can be really hard. In our paper, we suggest that learning to communicate about shared abstractions, like a roux, requires coordination at two different levels. First, we need to coordinate our concepts. We need to represent new abstract procedures in terms of the same sequence of goals and sub-goals as our partner, melting the butter, mixing in the flour, and so on. And second, in order to talk about these new concepts with one another, we need to coordinate our language, mapping the same words onto these abstractions. In other words, we need to form new ad hoc conventions. So to explore this idea in the lab, we began by designing a structured collaborative task where individual actions could plausibly be chunked into abstractions over time. We then analyzed behavior and language to understand how abstractions emerged at both levels in our dataset. And finally, we aim to explain these behavioral results with a novel computational model combining a Bayesian concept learning algorithm with a probabilistic model of convention formation in communication. Okay, so how can we bring this complex phenomenon into the lab? We couldn't get rats to cook, but we realized that a tower assembly task captured most of the properties we wanted. Specifically, we paired participants up for a real-time interactive task over the web. They were assigned to either the role of architects or builder and had to work together to build a tower. And importantly, these roles were asymmetric. So the architect viewed a scene, but was unable to place blocks, and the builder was given a fixed inventory of these little dominoes, but couldn't see what they were supposed to be building. So they had to rely on communication. So here's an example of a pair of participants taking turns in this environment. The goal of the architect was to use this chat box to give instructions in natural language. So they might say something like, place a red block on the left-hand side or build a C on the left. And the builder's goal was then to use these instructions to place blocks and reconstruct the target scene as accurately as possible. So the architect could see where blocks were placed, and both participants received feedback at the end of the trial. Now, our stimuli were hierarchically structured. So each scene contained two basic towers, and each tower contained exactly 4 blocks. And we designed a trial sequence to hit each combination of these towers in a random order. So for example, the first 3 trials might be scenes like this. So you get the C and the arch, and then the L and the C, and then the L and the arch in some order. And importantly, to examine how behavior changed as participants learned to collaborate better, we repeated each pair of towers 4 times across these 4 different repetition blocks for a total of 12 trials. So now we have this nice behavioral paradigm allowing us to study how collaboration changes with experience. But what did we find? Well, first, to get a sense of the data, here are some example instructions that different architects sent to their partners. And I've organized these such that each column is a different speaker, a different pair in our data set, and time unfolds from the top to the bottom. So the first row is the first instruction that was sent down to the final instruction that was sent. So in the first trial, architects tended to provide fairly similar instructions, usually referring to blocks individually. For example, place a horizontal block on square 11 or in the middle of the red dash on the first line, because we had little markers so that they had some reference points. Now, by the middle of their interaction, this first architect began referring to structures simply by their shape. So they called it a house-like structure. And by the end, they developed a pretty concise label for each tower. For example, an L. And interestingly, as you can see here, each pair actually developed fairly different kinds of shorthand by the end of the experiment. Okay, so more quantitatively, we found that human dyads were really good at this task, reaching nearly ceiling performance while relying on more concise messages over time. And we also found that the contents of these messages changed over time. So this shows the proportion of different words at the beginning to the end of the game. So some words referring to horizontal and vertical blocks became much less common, as well as the word block, while words naming entire towers, for example, L, C, and U, became more common. And this lexical shift suggested that referring expressions may gradually increase in abstraction from the level of single blocks to entire towers. And to test this hypothesis, as shown in this bar plot on the right, we asked independent raters to annotate each message for whether they contained words referring to a single block, a single tower, or some of both. And we see that there's this gradual increase in the tower-only messages from the first to fourth repetition. Okay, so we thought this was a really rich, exciting data set, demonstrating that people not only are able to learn to chunk new conceptual abstractions given experience in a task, but are also able to coordinate on ways of referring to these abstractions with language. Finally, we wanted to explain the cognitive processes giving rise to these phenomena. And in this last section, I'd like to share a computational model we developed to evaluate different hypotheses about how coordination and conceptual abstraction work together. So going back to this intuition that coordination needs to happen at two different levels, our framework integrates two basic modules drawing from recent breakthroughs in the modeling literature. First, we capture the idea of forming new conceptual abstractions in a probabilistic program learning framework. And we capture the idea of coordinating language with a probabilistic model of convention formation in communication. So I'd like to introduce these ideas starting with a basic pipeline of what problem we think we need this model to solve. So we start from this raw scene input viewed by the architect, just a bunch of pixels in a grid. And we need the architect to represent that in terms of some concepts in their own mind that captures the structure of this scene. And then the architect needs to have some mapping of those concepts to elements of their language that they can utter out loud. So they can plan their utterance, and then they produce a message that the builder takes as input and needs to interpret back into concepts in their own minds that then they can use to execute a motor program that produces a scene on their side that we can then compare with the original scene input that the architect saw. Now we can break this pipeline up in a couple of ways to understand this problem. So importantly, we have this distributed problem, which is that the things on the top belong in the architect's mind and the things on the bottom belong in the builder's mind, and they don't have access crossing these boundaries. What do we actually choose for these representations in each of these boxes? Well, for concept representations, we maintain a library of executable programs. So these are basically ways of re-representing a scene in terms of motor programs that could produce that scene. And then the language representation needs to be able to convert from elements of the program and elements of language that you can produce out loud. So we're going to call this thing on the left library and the thing on the right lexicon. But the kind of key area of innovation in this project is that learning needs to take place over time. So as a pair sees more trials, observes one another using language, these representations in each person's mind need to be updated. So how do we do this? So let's begin with this library learning problem on the left-hand side, which is essentially the problem of how do we form new conceptual abstractions based on data. So our proposal here begins with this Dreamcoder model proposed by Kevin Ellis and colleagues. You start with a base library of primitives that can be combined together to generate different block structures in little programs. And as you progress through multiple trials of tower scenes, you engage in this process of abstracting common subroutines, allowing you to re-represent your data more efficiently. And formally, this model proposes a set of candidate subroutine fragments, F, after each trial and updates your posterior score over possible ways of extending the library. So you're basically trying to make a decision about should I add this fragment to my library or not. And this decision is guided by a likelihood, which uses the minimal description length of the data under this updated library. So basically, can I explain previous towers more efficiently with this new library, as well as a prior that captures a preference for smaller libraries. So just as an example, let's see what happens when the agent sees these first two trials. So you can represent these as executable sequences of motor actions in this little world. And then you can propose fragments from these different programs and score them. So intuitively, the sequence in orange is this highest scoring fragment, which corresponds to this C shape, which may help you on future trials since you can now plan over these higher order abstractions rather than these low-level motor commands. Okay, so now we have a model of how abstractions are formed in individual agents' minds, but now how do they communicate about them? So this leaves the problem of convention formation. In order to capture this communication aspect of the problem, we draw on the Rational Speech Act model. Both agents need to maintain uncertainty about new words that are introduced. And how do they decide what utterances to emit? Well, the builder is assumed to say for each word in this utterance, what action should I take? And then the architect is trying to produce utterances to create a tower relative to its utility. And this utility is defined according to these Rational Speech Act models in terms of two considerations: an informativity consideration, as well as a cost consideration. So all other things being equal, the architect would prefer to emit shorter utterances. Okay, so this is how they make decisions about production, but this is relative to their current lexicon. So over time, as they gain additional observations of how their partner is behaving, they can update their beliefs about the lexicon. So importantly, this needs to happen for new symbols that are arising in their libraries. They need to be able to bind these to words in some way. So this creates a coordination problem. I invite you to see our paper for additional details on how these updates work. Okay, so we now have a pair of agents that both update their conceptual representations of the scene as well as update their beliefs about what their partner's language means. So we ran our model on all trial sequences seen by participants in our task and manually categorized the fragments that were learned based on their level of abstraction at the sub-tower level as well as the tower level. So we can see that these tower level abstractions are acquired around the second repetition block. So by this point, both the speaker and the listener have these abstractions coming online in their conceptual repertoire. But what did they actually say? Well, we find that the architect gradually shifts to higher level descriptions as a function not only of these new abstract primitives coming online, but also as uncertainty about the ability of their partner to interpret these more abstract tower level utterances goes down. So this qualitative pattern matched our empirical data quite well. Okay, so in this project, we were able to not only elicit these rich behaviors of coordination over time, but explain them as a combination of the ability to learn these program-like abstractions, as well as coordinating on linguistic tokens. Thanks very much for your attention.